Hello students. Today we are going to study the binomial theorem from class 11. The main concepts are covered and all the different types of examples will be explained. So watch the video till the end. The statement of the binomial theorem. For any positive integer n, a plus b raised to n is equal to nc0 a raised to n plus nc1 a raised to n minus 1 into b plus nc2 a raised to n minus 2 into b square and so on up till ncn b raised to n. Now the proof of this theorem, we are going to see how it is proved. First of all, we are going to prove this theorem by the principle of mathematical induction. What is the principle of mathematical induction? If you want to prove a statement for an integer n, then first you prove the statement is true for n is equal to 1. Then assume that the statement is true for some n is equal to k, and using that show that the statement is true for n is equal to k plus 1. If this can be done, then we can say that for any n, any positive integer n, the statement holds true. So this is the principle of mathematical induction. Now what is our statement? Our statement denoted by P of n is the binomial theorem, a plus b raised to n and its expansion, that is the binomial theorem. So first of all, for n is equal to 1, what is P of 1? A plus b raised to 1. That is same as a plus b. Can we write a plus b as 1c0 a raised to 1 plus last term will be 1c1 b raised to 1. So yes, it holds true for P of 1. Now assume that the statement is true for some positive integer k. What does that mean? A plus b raised to k is equal to kc0 a raised to k plus kc1 a raised to k minus 1 into b up till kck b raised to k. So we are assuming that the statement is true for some k, and we will prove that it is also true for k plus 1. So now what is the statement for k plus 1? A plus b raised to k plus 1. So what we have to prove is a plus b raised to k plus 1 is equal to k plus 1 c0 a raised to k plus 1 plus k plus 1 c1 a raised to k into b up till k plus 1 c k plus 1 b raised to k plus 1. Now a plus b raised to k plus 1, the left hand side can also be written as a plus b into a plus b raised to k. So now we will use the assumption of our a plus b raised to k. So using that assumption, a plus b raised to k plus 1, we have written as shown in the statement 1. Now 1 by 1 just multiply a and b with the second part of the statement. So first term will be kc0 a raised to k into a. So how can you write that? Kc0 a raised to k plus 1. Second term will be a into kc1 a raised to k minus 1 into b. So how can you write that term? kc1 a raised to k into b. Similarly, afterwards we multiply by b. So what will that be? The term in that will be b into kc0 a raised to k. Similarly, next term kc1 into a raised to k minus 1 into b square and so on. And what will be the last term? kck b raised to k plus 1. So what we have obtained is kc0 a raised to k plus 1. We take out the terms having a raised to k into b. So what do we have? A raised to k into b into kc1 plus kc0. But what is kc1 plus kc0? If you remember in the last video for combinations, we had seen that kc1 plus kc0 can be written as k plus 1 c1. Correct? So what do we have? K plus 1 c1 into a raised to k in b. The third term k plus 1 c2 a raised to k minus 1 into b square. And the last term k plus 1 c k plus 1 b raised to k plus 1. So now what we have shown is the statement is true for k plus 1. Thus it has been proved that P of k plus 1 is true whenever P of k is true. Therefore, by principle of mathematical induction, P of n is true for every positive integer n. This principle of mathematical induction is very useful for proving statements of this type. The binomial theorem can be stated in short as a plus b raised to n is equal to summation k running from 0 to n nck a raised to n minus k into b raised to k. The coefficients occurring in this expansion are known as the binomial coefficients. Now there are some special cases which are derived from this. First one is x minus y raised to n can be written as nc0 x raised to n minus nc1 x raised to n minus 1 into y plus nc2 x raised to n minus 2 into y square and so on, plus minus 1 raised to n ncn y raised to n. That means in short, plus minus alternative sign will be there for x minus y raised to n type of expansion. Now suppose if you want to expand 1 plus x raised to n, then it will be just you have to take a is equal to 1, b is equal to x. So it will be nc0 plus nc1 into x plus nc2 into x square up till ncn into x raised to n. And suppose you want to expand 1 minus x raised to n, on the similar basis it will be nc0 minus nc1 into x plus nc2 into x square minus, that means again plus minus will be repeated alternatively. Also remember nc0 and ncn are 1. This we know from the combinations. An interesting fact, the coefficients in the binomial expansion are the numbers which appear in the corresponding rows of the Pascal's triangle. Now if you observe the Pascal's triangle is given over here, how this is formed? You have ones on both the side of the triangle. In between rows, you get by adding the elements above them. Like for example, 1 plus 1 is 2. Then in the next row you have 1, 3, 3, 1. How did you get that? 2 plus 1 is 3. In the next row you have 1, 4, 6, 4, 1. How did you get that? 3 plus 1 in the above row gives you 4. 3 plus 3 in the above row gives you 6. And again 3 plus 1 in the above row gives you 4. This is how you get by adding the elements in the row above. Now let us see how Pascal's triangle and binomial theorem are related. You know the expansion of a plus b whole square. It is a square plus 2ab plus b square. Now if you just look at the Pascal's triangle and if you see the second row, what do you get? 1, 2, 1. So same are the coefficients of a plus b whole square. Then you know a plus b whole cube is a cube plus 3a square b plus 3ab square plus b cube. Now just observe the third row for this Pascal's triangle, 1, 3, 3, 1. So same are the coefficients of a plus b whole cube. Now suppose if you are asked to find a plus b raised to 4. Remember you don't need to do any other calculations if this triangle is understood. What is the next row? It is 1, 4, 6, 4, 1. Correct? So just put the coefficients. So a plus b raised to 4 is nothing but a raised to 4 plus 4a cube b plus 6a square b square plus 4ab cube plus b raised to 4. So this is how Pascal's triangle and binomial theorem are related. Let us see the examples. Example 1. Expand x by 3 plus 1 upon x whole raised to 5. You know the binomial expansion. I have just given the formula over there. Now let us put the values. First of all, you start with 0. So 5c 0, x by 3 raised to 5, 1 upon x raised to 0. Next term 5c 1, x raised to 3 raised to 4. X upon 3 raised to 4 into 1 upon x raised to 1. Third term 5c2, x by 3 cube into 1 upon x square. Then plus 5c3, x by 3 square into 1 upon x cube. Plus 5c4, x by 3 raised to 1 into 1 upon x raised to 4. And last term 5c5, x by 3 raised to 0 into 1 upon x raised to 5. Now you know how to simplify the combinations. We have just seen in the previous video. You know NCR is what? NCR is n factorial upon r factorial into n minus r factorial. So just expanding that and simplifying, what do we get is x raised to 5 upon 243 plus 5x cube upon 81 plus 10x upon 27 plus 10 upon 9x plus 5 upon 3x cube plus 1 upon x raised to 5. Example 2. Using binomial theorem, evaluate 96 raised to 3. So now 96 raised to 3 can be written as 100 minus 4 raised to 3. So we will use the expansion of the type x minus y raised to n. So first term 3c0 100 cube into 4 raised to 0 minus 3c1 100 square into 4 raised to 1 plus 3c2 100 raised to 1 4 square minus 3c3 100 raised to 0 4 cube. Remember, when it is minus sign in between, the plus and minus occur alternatively. So when you simplify this, see how easily 96 cube can be obtained. It is equal to 884736. Example 3. Find a plus b raised to 4 minus a minus b raised to 4. Hence, using it, evaluate root 3 plus root 2 raised to 4 minus root 3 minus root 2 raised to 4. The first thing is we will expand a plus b raised to 4 and then a minus b raised to 4 using the binomial expansion. So the formulas are given over here. Just put the formula over here. So a plus b whole raised to 4 minus a minus b whole raised to 4. After simplification, you will see that which terms will be remaining. 2 into 4c1 a cube b plus 4c3 ab cube. So this is 2 into 4a cube b plus 4ab cube or 8ab into a square plus b square. So the simplest expansion we have obtained is 8ab into bracket a square plus b square. Now just put a is equal to root 3 and b is equal to root 2. So you will get that equal to 40 into root 6. It is just the application of the formula, but be careful with the calculations. Next example. Using binomial theorem, indicate which of the following is greater, 1.1 raised to 10,000 or 1,000. So simply what you can do is 1 plus 1 raised to 10,000 can be written as 1 plus 0.1 raised to 10,000. Now apply the binomial expansion of 1 plus x raised to n. So first term will be 10,000 c0, second term 10,000 c1 into 0.1 raised to 1. Why? Because 1 raised to anything is always 1. So this will be the first two terms, and plus other terms which will follow will obviously be positive terms. First term NC0, you know that is equal to 1. So 1 plus second term NC1 is n. So it is 10,000 into 0.1 raised to 1 means 0.1. So this is nothing but 1001, which is obviously greater than 1000. So we can say that 1.1 raised to 10,000 is greater than 1000. This type of examples are also asked. Next type of example. Using binomial theorem, show that 9 raised to n plus 1 minus 8n minus 9 is divisible by 64 whenever n is a positive integer. Now see, looking at the problem, what we need to show is it is divisible by 64, means the left hand side is a multiple of 64. So what we need to show is 9 raised to n plus 1 minus 8n minus 9 is equal to 64 into sum k. Now just simplify 9 raised to n plus 1. How can we write? See, you have 9, 8, this side you have 64. So looking at this, it is very easy to understand that we have to write 9 raised to n plus 1 as 1 plus 8 raised to n plus 1 and then apply the binomial expansion of 1 plus x raised to n. Instead of n, you are having the last term as n plus 1. So when you put that in the formula, you will get n plus 1 c0 plus n plus 1 c1 into 8 raised to 1 plus n plus 1 c2 into 8 square up till n plus 1 c n plus 1 into 8 raised to n plus 1. Now just simplify this and just bring the terms having 64 together. That means all the terms after the first two terms will have 64 and then other powers of 8. So you can write this as 1 plus n plus 1 raised to n plus 1 into 8 plus 64 into n plus 1c 2 up till n plus 1c n plus 1. Last term will be 8 raised to n minus 1. This is also obvious because you are taking out 64 or 8 square outside. So n minus 1 plus 2 is nothing but n plus 1. So this is how you have to just group the terms. So what you are having is now 9 raised to n plus 1 is equal to 1 plus 8, that is 9, means 9 plus 8, 10 plus 64 into some terms. So you can say 9 raised to n plus 1 minus 8n minus 9 is equal to 64 into some positive terms. So we can say that 9 raised to n plus 1 minus 8n minus 9 is divisible by 64. Next example. Using binomial theorem, prove that 6 raised to n minus 5n always leaves remainder 1 when divided by 25. Now we have the fundamental theorem, if you remember, which we have already studied in previous standards. For two numbers a and b, if we can find numbers q and r, q is the quotient, r is the remainder, such that a is equal to bq plus r. Here, in order to show that 6 raised to n minus 5n leaves a remainder 1, that means the value of r is 1 when divided by 25. What do we have to show? 6 raised to n minus 5n is equal to 25 into some k plus remainder 1. Correct? If we can show that 6 raised to n minus 5n can be expressed in the form of 25k plus 1, then the above proof is valid. So now by the binomial theorem, we already have the binomial theorem for sum 1 plus a raised to m. Take a is equal to 5 in this case. So what do we have? 6 raised to n is 1 plus 5 raised to n. We can write 6 raised to n as 1 plus 5 raised to n. So that will expand as 1 plus 5n plus nc2 5 square plus 5 raised to n. Now again, like the previous example, we are taking out 5 square common from third term onwards. So it will be 1 plus 5n plus 25 into nc2 up till 5 raised to n minus 2. So what do we have? 6 raised to n minus 5n is equal to 1 plus 25 into some positive term. Hence we have shown that it leaves a remainder 1 when divided by 25. The basic concept of binomial theorem is discussed in class 11, and we have seen the different types of examples which can be asked based on that. Some assignment examples: if a and b are distinct integers, prove that a minus b is a factor of a raised to n minus b raised to n whenever n is positive integer. So again, looking at the sum, it should be understood that a raised to n can be written as a minus b plus b whole raised to n, and then you expand using the binomial expansion. Second example, prove that summation r running from 0 to n 3 raised to r into NCR is 4 raised to n. Now again, as I am telling you, just look at the example and see how you can use the binomial expansion. 4 raised to n can be written as 1 plus 3 raised to n, and you will get this proof. We have discussed the binomial theorem from class 11. Hope the concept and examples are understood. Please like and share the video and subscribe to the channel. Thank you.